And in our last demo, what I have is some hydrogen peroxide. And so we're going to write out a word description on this one. And we'll say, hydrogen peroxide decomposes in the presence of. And what we're going to do is we're going to add this stuff, which is manganese 4 oxide. So this is going to decompose in the presence of a manganese 4 oxide catalyst, yielding liquid water and oxygen gas. Now, of course, we introduced one new word in here, and that is the word catalyst. And what is a catalyst? Speeds up a reaction. Exactly. With this caveat, we say it speeds up a chemical reaction without being consumed. Which means if we start with 5 grams of it, at the end we're going to have 5 grams, exactly. So now to do this one, I'm going to take this pop bottle that I just took out of the recycle bin over here, and I'm going to put this into this beaker, and I'm going to add some hydrogen peroxide. Now, how many used hydrogen peroxide before? What do you use it for? Cleaning wounds, exactly. And some of you might use it for something else. You go to the salon. Well, some of you might do it at home.
Hair bleach?
Hair bleach, yes.
I just got my hair bleach.
Okay. And it depends upon the concentration. This stuff, though, is stuff you probably wouldn't use. This is 30%. The stuff you put on your skin if you have a wound is 3%. Okay, so this is about 10 times more concentrated than the stuff you put on your skin. Okay, but we're going to see why it's effective. First of all, there's part of the reason why I put this into a beaker. You notice now that I placed it in this beaker so it fits very nice and snug into here. And then we're going to go ahead and add the catalyst to this. Oh, and before I do that, you're going to have to close your eyes and make a wish. If you can open back up. That's my genie in a bottle. Okay. Now, do you see what happened? Remember how it fit in there before? Now, if you ever wonder how that works, what I'm going to pass out here is these are molds that are used to make pretty much all pop bottles. And the way that you make them, actually, is you inject them into a mold, and the mold will take on the shape of whatever container you want, and then you basically blow steam into it. You blow steam into it, it expands and fills that up, and then they cool it back down, and it takes on the shape of whatever bottle you want. But almost all bottles will start off as that shape right there, and by blowing hot steam into it, you get the shape of the pop bottle that you want. Now what happens when you heat it back up like we did here, this is something now that's very, you feel it.
It's pretty warm.
Yeah, it's pretty warm. What happens once you heat it back up, it will wind up shrinking back down to its original size. Yes?
It has like a handle, then does it have a tube with a handle on it?
Someone would have a handle?
Yeah, like milk jug.
Like a milk jug, that's a different plastic.
Okay.
It's a different plastic. So this one here I don't remember now. I should know my polymers. I don't, but it's a different plastic
Yeah.
on the milk jugs.
But are they made the same way?
They made it. No, they're made in a different way. And this I know because I worked in the plastic factory. Okay. So, but that's what's called a preform mold, and you go ahead and then stick it in there, and again you just blow steam into that. Now we need to wrap up here though with a chemical equation. So we want to write out an equation for this. Oh, and by the way, what's another catalyst do you think for this reaction? Blood. You have an enzyme in your blood, that's another catalyst. You can throw in a chunk of meat, it'll work the same way. Okay? And that's why you get the fizzing, why you put it on a cut. It will fizz and bubble and everything, and that winds up cleansing your wound. And it's actually the oxygen that's in there that does the cleansing, and it kills some of those bacteria. But now to write out the equation. Anybody know the formula for hydrogen peroxide?
H2O2?
Yes, but you don't actually need to know it.
H2O2.
It's H2O2. And anybody know where we write the catalyst? Catalyst goes above the arrow. And the catalyst here is manganese 4 oxide. So if we want to write the formula for manganese 4 oxide, that means we have manganese with the charge of 4 plus. From the periodic table, we saw that oxide is O with a charge of 2 minus. So it's Mn with 4 plus, O2 minus. The formula for manganese 4 oxide is MnO2. MnO2. And then our products. We say it yields liquid water. So liquid water is going to be H2O, liquid. And then the other product is? No. It is oxygen gas. And the formula for oxygen gas is O2, the gas. Our first question on the Socrative app on Tuesday is going to be balance this equation. Okay? We'll go 5, 4, 3, 2, 1. Correct choice is E. Now, two of these choices could never be possible for any balanced chemical equation. And which two choices would never be possible for any equation? Yeah, anyone here with the zeros. Okay, because a coefficient can never be 0. Yeah, if we don't write any coefficient in, which coefficient is implied? 1. So if you have put zeros in here, then you would be incorrect. Now the next, and how do we arrive at that? Well, if you look at the strategies that I passed out here, these are ones that we alluded to last class, but you did not have them, and we kind of apply them in this order. That is, we always save the simplest formula or element to balance last. We use the least common multiple between two numbers. Third one is to use fractions when necessary to balance the equation, then multiply through by an integer to remove the fractions, and then one here that I like to call even odd. And these two here are often used interchangeably. So as I look at this particular one that we just have, and since several of us did get this one wrong, we might as well go through it. As you look at this one, we save the simplest element or formula to last. Which one of these should we save to last in this equation? Well, the simplest would be
O2.
O2 right here. So that means we should then go ahead and start by balancing the hydrogen. So we look at hydrogen. How many on the left? How many on the right? 2. Okay, so 2 and 2, that's balanced, which then takes us back to oxygen. How many oxygens on the left?
2.
And how many on the right?
3.
3. Okay, so now, in order to balance this, that means since there's only one element in here, we should be able to put some sort of coefficient in front of the O2 in order to balance this equation. Now, for some of you, this should be very apparent. If it's not apparent, then remind you again, how many oxygens are there right here? There's 2. How many oxygens in this formula?
1.
1. And how many oxygens in this one?
2.
2. All right, so now, if there's 2 in there, we know we're going to have to put some number here in front of the O2 in order to balance it. We could go ahead and call that value x. We don't know what x is, so we're going to find it. So remember that coefficients stand for multiplication, and so this would be the same as 2 times x. And of course, whatever is on the right-hand side must equal whatever is on the left-hand side. So this becomes a very simple algebraic equation to solve for x. If we want to solve this for x, we can then subtract 1 from each side. Subtract 1 from each side, then on the left-hand side we get 1. On the right-hand side, 1 minus 1 gives us 0. And we're left with 2x is equal to 1. Which means then x is equal to how much? Again?
1/2.
1/2, exactly. We divide each side by 2 and find out that x is equal to 1/2. And so we can balance this then with a coefficient of 1/2. However, we can't leave fractions in here. When we balance equations, we always use the lowest whole number ratio of coefficients. So then we have to multiply by some value that will get rid of that fraction. And which integer can we multiply by here? And if we multiply by 2 and we distribute that across the parentheses, the coefficient in front of the H2O2 would become 2. The coefficient here would become 2. And 2 times 1/2 gives us 1. Again, though ones are implied, we don't write them. And so this then winds up being that balanced chemical equation. So that's a way we can balance this using fractions. Another way we can wind up balancing this one, we go back to the very beginning, we look at strategy number 4. And this is the one that we call an even-odd strategy. And this one here, if we go back to our equation, we count those number of oxygens. Again, how many oxygen atoms are there on the right-hand side?
3.
And how many oxygens on the left?
2.
Okay, so now, regardless of the integer we put in front of here, whether it's 1, 2, 3, 4, 5, whatever, the number of oxygens on this left-hand side will always be which type of number?
Even.
Always be even. This side we have an odd number, so we need to turn an odd number into an even number. In order to turn it into an even number, what type of coefficient must go in front of the H2O2? Well, does it have to be an even one or does it have to be an odd one?
Even.
It has to be even, because an even number times an odd number is always going to give you an even number. And so if we're going to make an even number on this side, we have to put an even number in front of the H2O. So then what you do here is you just try different even coefficients. If 2 doesn't work, you try 4. If 4 doesn't work, you try 6. And you just keep going on in order to make an even number on the right-hand side. So let's start with the smallest even number, which is 2. Once we put that in front of there, we have 4 hydrogens. We have 2 oxygens here, plus 2 more here for a total of 4. So since we have 4 hydrogens, 4 oxygens, we can make the same number of oxygens and hydrogens on the left-hand side by putting a 2 in front of them right there. The techniques that we use to balance is called balancing by inspection, which is just a funny name for trial and error. If you try something that doesn't work, you try something else. And some of the ways to reduce the number of trials is to use these strategies right here. When you balance them in mastering chemistry, it's always going to look for the smallest whole number ratio. So while it would be correct if you balance it like this, 4 and 2, this is balanced. This is not the smallest whole number ratio. So if we want the smallest whole number ratio, we take all of these coefficients here and
Divide by 2.
divide them by 2. And so whenever you look at your answers in Mastering Chemistry, you're always looking for that smallest whole number ratio. And come exam time in here, generally you'll get close to full credit if you haven't reduced them to the smallest whole number coefficients. There might be like a 1 point deduction out of 3 or 4 that you might get if you've not reduced them down. So any questions on this one? Okay, next up then we have this equation here. We balance this one. This one is the next one on the Socrative app. So it says when balance using the smallest whole number coefficients, the coefficient of NH3 is by the way, if these would show up as multiple choice questions on an exam, this is a possible way that they could show up. Let's take about 30 more seconds. Get your equation balanced. Take about 10 more seconds. Lock in your answers. We'll count down here. 5, 4, 3, 2, 1. And the correct answer here is 4. Now, if we want to arrive at this particular answer, then what we're going to do is to come back to this one. We want to make sure that the, let's see, probably the best one to leave to last is going to be N2 because this is the simplest, which means we should then try to balance the hydrogens. So which strategy of those 4 would be best to balance hydrogens here? Well, even odd could be one. I would look to another one though, actually. Least common multiple would be another one. I try to apply them as we go down, because if we look at this one, we have 3 and 4, and even odd would work, but we could apply the least common multiple with this one right away. What is the least common multiple between 3 and 4?
12.
Okay, so if we want to make 12 hydrogens, what coefficient do we need right here?
3.
3. In order to make 12 hydrogens on the right-hand side, what coefficient do we need here?
4.
We need a 4. Once we put that in, we have 12 hydrogens and 12 hydrogens. Then we check the nitrogens. We have 6 nitrogens here. We have 4 here, plus 2 more for a total of 6. That makes us the balanced chemical equation. So this is as far as we're going to go with just simply balancing. Are there any questions on balancing chemical equations?